The hypothesis of the ancient infinite explosion is by and large recognized by most scientists as the fundamental explanation for the starting points of the universe, wrapping the creation of stars, planets, and all life in that, including us. Despite its decently capricious name, the term Big Bang suitably captures the monstrosity of the event. At first, the universe was a thick collection of particles squeezed into a space more modest than a pinhead. From this moment, a gigantic impact of matter occurred, known as the Big Bang. This briefly summarizes the communication that unfurled over billions of years. However, no matter what the persisting distinction of the hypothesis of how things became, movements in logical information have dynamically tested its expectations. When NASA shipped off the James Webb Space Telescope, the biggest and most high-level space observatory to date, researchers theorized that its perceptions would build up the hypothesis of the ancient vast explosion. Unluckily, after only 1 year in space, the telescope has stunned specialists with its pivotal capacities, giving unprecedented looks into the universe's past. The James Webb Telescope's revelations have uncovered systems so old that they could even reshape how we decipher the universe's beginnings. This surprising exposure has ignited serious interest among scientists and fans alike. One such critical divulgence came when astronomer Rohan Naidu, dissecting early pictures from the James Webb Telescope, coincidentally tracked down a system that shocked everybody. This universe, named Glass C13, appeared to be strangely monstrous and followed as far back as a brief time frame after the Big Bang, making it older than any previously seen world. Naidu's energy was substantial as he conferred the discovery to colleagues in the world, describing it as beyond anything space experts might have ever imagined. The James Webb Telescope, situated far away from normal interference and outfitted with best-in-class advancement, was designed to jump into the universe's earliest age known as the Grandio Dawn. This period, covered in mystery, marks the development of the universe's most important stars and galaxies. By examining systems from this period, scientists hope to refine how they interpret major astronomical cycles like the effect of matter and dark energy. Initial assumptions for the James Webb Telescope's revelations were modest, expecting only a few weeks' worth of distant universes. However, the truth outperformed all projections. The telescope's photos uncovered systems of astounding development, testing existing models and inciting a hurricane of assessment, as specialists continued to analyze the James Webb Telescope's data. The consequences of these discoveries could be critical, presenting a new era of cosmological appreciation. The amazing revelations from this significant observatory offer an enticing glimpse into the universe's past, driving humankind's journey to unravel the secrets of existence. As early systems emerged, researchers and observers wound up in a scramble to figure them out. Could this gathering of strangely colossal and brilliant early universes be whimsical, perhaps due to flaws in the assessment of the telescope's initial discernments? Or, if legitimate, could they somehow be accommodated with standard cosmological models? Very possibly, were they the fundamental hints that the universe is more interesting and complex than our boldest theories had expected. The question is nothing less than how we would interpret how the exact universe we know emerged out of the primordial chaos. The early exposures from the James Webb Space Telescope might potentially overhaul the starting pieces of Grandio history. These areas concern faraway ages in distant systems as well as our own presence here in the normal, smooth way. As Mark McCarran, a senior scientist at the European Space Agency associated with JWST, remarked, "You assembled these machines not to confirm the perspective but to break it. You simply don't know how it will break in a manner. JWST's view of early universes has been billions of years in the making." However, more subtly, they trace back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was still a few years away from its debut. Even then, the Institute's then director, Ricardo Jahn, asked his team to start considering what might come after Hubble. Much further away from starting disputes over focusing on Hubble, Jahn was relentless in predicting the broad development process. Fellow scientists, including Deputy Administrator of SD Sky, along with a small group, began drafting ideas for what would eventually become the modern Space Telescope, later renamed JWST. They noticed that while Hubble would be remarkable, its abilities would be limited by its observations in visible light. The NGST Next Generation Space Telescope, by contrast, would observe in the infrared range, allowing it to peer deeper into the universe. The need for JWST became even more clear in December 1995, when cosmologists coordinated the Hubble Deep Field observation. Despite expectations of finding only a few faint massive systems, the resulting image uncovered countless galaxies stretching back more than 12 billion years into the universe's past. After more than 20 years of development and at a cost of around $1 billion, JWST was finally launched on Christmas Day 2021. The telescope. The James Webb Space Telescope JWST underwent rigorous testing before reaching its operational space position. By July 2022, it was ready to begin its expected first year of scientific observations, known as Cycle 1. Some of JWST's initial mission was dedicated to high-impact programs, including cosmic evolution, early release science reviews, and the GRIS point of convergence, all of which aimed to uncover secrets about the early universe. Astronomers dedicated countless hours to scanning patches of the sky in search of early universe systems, initially expecting modest discoveries like a more detailed version of the Hubble Deep Field. However, they were in for a shock. Stephen Balance-Lynn from the University of Texas at Austin, leading the SEA project, assumed that extremely distant systems should only emerge after several data cycles from various initiatives. To cosmologists' surprise, these universes appeared rapidly. The record for the most distant known galaxy had previously belonged to GNZ 11, seen in 2015 with a redshift of 11. Redshift measures the stretching of light due to the universe's expansion, with a higher value indicating a greater distance. But from the first set of GLASS C13 observations, two separate groups, including one led by Rohan Natu, independently identified GLASS Z13 with a redshift of 13, pushing the timeline back even further. In their scramble for quick results, experts relied on redshift estimation techniques based on brightness measurements rather than more time-consuming direct assessments. Despite their limitations, these assessments revealed universes that were unexpectedly bright and massive, some possibly boasting a mass equivalent to 1 billion suns, similar to our galaxy. The discoveries didn't stop there. In the following days, various universe contenders from the Sears and GLASS groups emerged, some with redshift values as high as 20, indicating they existed just a brief time after the Big Bang. These galaxies displayed disk-like structures, which were not expected at such early galactic ages. Moreover, another group found evidence of smooth galaxy systems at a redshift of 10, less than 500 million years after the Big Bang. The rapid rise of sizable galaxies challenges the assumptions of the standard cosmological model, lambda cold dark matter LCDM. To grasp this phenomenon, a brief return to early universe components is essential. In the early minutes after the Big Bang, the universe was a hot, thick soup of primordial particles. As the universe expanded and cooled, helium and other light elements formed, leading to the emergence of the first particles about 400,000 years later. Roughly 100 million years after the Big Bang, conditions became favorable for the formation of the first stars, composed primarily of hydrogen and helium. These early stars, larger and more massive than current stars, gathered into protogalaxies, organized by the gravitational pull of dark matter. However, JWST's discoveries challenged this model, revealing massive galaxies far earlier than expected. Stacy M. from Case Western Reserve University observed the alarming shortage of smaller, more modest protogalactic components, suggesting that some of these galaxies might be closer than previously believed, hidden by dust and appearing dimmer and more distant. The discovery of these early universes raises significant questions about the universe's origins, highlighting the need for continued investigation and correction of our cosmological models. Follow-up observations of GLASS C13 in August 2022 by the Atacama Large Millimeter Array ALMA in Chile cast doubt on the initial findings. Despite using brightness-based methods, ALMA did not detect significant amounts of buildup associated with GLASS C13, RSP. Tom B. from Goya School, who led the observations, said, "This suggests that low redshift interlopers can be ruled out." However, ALMA failed to identify the galaxy altogether, illustrating the challenges of confirming observations made using JWST's advanced capabilities. Rohan Natu, one of the experts in question, raised concerns about the consistency of the situation, stating, "The good news is there's nothing recognized. The bad news is there's nothing related to JWST's own insights." The most concerning explanation could be that the standard LCDM cosmological model requires updating. Michael Bohan Colin, a cosmologist, emphasized the size of this potential shift in perspective, stating, "These results are very surprising and hard to fit into our standard model of cosmology. It would be a real revolution." One tentative suggestion is modified Newtonian dynamics MOND, which challenges the existence of dark matter. JWST's insights could lend support to MOND, as proposed by Mark McCarran, though not all cosmologists are convinced of its legitimacy. Another possible explanation is that early universe galaxies could have had very little buildup, making them appear more astonishing and affecting mass calculations. This situation could also explain the difficulty in detecting glass C13. Charlotte Brickley and her colleagues proposed that JWST might be observing the most impressive young galaxies in the early universe, suggesting star formation conditions during that era were more efficient due to higher gas pressures and temperatures, possibly influenced by early gravitational fields. The rapid dissemination of research papers from JWST's initial observations reflects a shift toward continuous peer review through platforms like virtual reality, speeding up the flow of discoveries. While this accelerates the spread of revelations, there are concerns about rushing conclusions before thorough analysis. Despite potential recalibrations, it is unlikely that all the high redshift galaxies seen by JWST will be invalidated. In fact, the sheer number of these galaxies suggests that the early universe may be very different from what was previously expected. Finn Lin expressed confidence in the validity of the discoveries, stating that the chances of cosmologists being totally mistaken are slim. Stargazers are currently racing to confirm subsequent observations with JWST. Nancy Levinson is evaluating about 12 proposals from various groups seeking additional JWST observation time to study high redshift galaxies. Given the excitement and importance of these early discoveries, confirming them is crucial. Projects like the Universe Web, led by K2T, aim to expand the known population of early galaxies by observing a broader area of the sky for longer periods. These initiatives hope to identify many more galaxies, with other efforts focused on searching for evidence of the first protogalaxies, possibly using the spectacular deaths of supersized first stars and their associated stellar explosions as markers for their existence. Some assessments suggest that JWST could detect galaxies with a redshift of 26, just 120 million years after the Big Bang. Confirming even a small number of these high redshift newcomers would be a major achievement, according to Naitu. He suggests that cosmologists are not discouraged by their findings. JWST has ushered in a new era of science, and despite its limitations, the rapid exchange of new data has energized astronomers. Troy, who introduced one of the proposals, highlighted the importance of confirming these discoveries as JWST embarks on its mission to explore the universe. Researchers eagerly await what new revelations lie ahead. With each observation, we move closer to answering the fundamental questions of existence and deepening our fascination with the grand tapestry that surrounds us. In conclusion, the James Webb Space Telescope JWST has ushered in a new era of investigation and discovery, challenging how we understand the universe's origins and development. Its exceptional observations of galaxies formed shortly after the Big Bang have sparked excitement and debate among researchers, pushing the boundaries of cosmological knowledge. The telescope's ability to peer further into existence than ever before has uncovered cosmic anomalies that defy conventional models, prompting a re-evaluation of existing theories and the development of new ones. From ancient galaxies to the mysteries of dark matter and early star formation, JWST's discoveries have far-reaching implications for our understanding of astronomical history. Looking forward, JWST promises to continue unraveling the complexities of the universe, offering glimpses into realms previously beyond our reach. Its revelations not only advance scientific inquiry but also inspire awe and wonder at the vastness of the universe and our place within it. As JWST embarks on its mission to explore the universe, scientists eagerly anticipate the new discoveries that lie ahead, drawing us closer to unlocking the mysteries of existence and gaining a deeper appreciation for the cosmic story that unfolds around us.